so let's continue on then. So we're losing heat in the condenser because we've got the refrigerant so hot that it's hotter than the outside air. And then we kind of have this magic occur that we call the expansion valve. Now, we didn't get into compressible flow and supersonic flow and throttling. Suffice it to say, the goal here is to cause the pressure to drop. So basically, we squeeze this down and then we allow it to expand, and that causes a pressure drop. And when the pressure drops, the temperature drops. And the goal of this process is to get fluid coming out that is so cold that when we run it through another heat exchanger we call the evaporator, we want the refrigerant to be colder than the low temperature reservoir down here, so we will actually absorb heat from the low temperature source. You could use a turbine here. I think we talked about that. If you use a turbine here, this actually is the exact reverse. You see that in really large refrigeration units. In your household refrigerator, you don't want additional moving parts to fail, and you're not going to generate that much electricity off of a turbine in here, but you could put one in there. But again, if I'm moving massive amounts of heat, putting a turbine in there and extracting a little bit of work out to power some small devices would actually be pretty cool, and we see that sometimes. So the goal of the evaporator, so basically I'm bringing in typically some kind of a mixture. Maybe it's even all the way down at the liquid phase, but again, I've caused a pressure drop, which also causes a temperature drop in the refrigerant. So this is the low pressure side, and it's the cold side, and I get somehow through the expansion process, I get the temperature to drop. So the refrigerant is now cooler than the cold space, so the refrigerant will absorb heat from this cold space in the evaporator. And then the process is ready to repeat. Compressor takes the low pressure, low temperature refrigerant, adds some energy to it that increases the pressure, and if it's a vapor, it's going to increase the temperature. Then I've got screaming hot, high pressure refrigerant ready to go back and repeat the process. So again, the first law, if we add up all the energies here, this is, I've got a power input minus Q from Q at H and plus Q at L. I'm putting dots above these. You can put dots above them. You don't have to. You can work at per unit time or you can work at total amount. Either way is fine. But because it's a cycle, we'll set that equal to 0. So the power input equals Q dot H minus Q dot L. Okay. All right, so we don't normally talk about efficiency for a refrigerator. We talk about the coefficient of performance for the refrigerator. It's still going to be what you want, which in this case you want Q dot L. To get it, you got to put the power input to the compressor. Right? So this quantity is typically greater than 1. That's why we don't call it an actual efficiency. But if I substitute this in for the work in, then I get this expression 1 over QH over QL minus 1. Okay. And again, the maximum performance I can expect out of a refrigerator would be the reversible device. By definition of reversible, it means it's the best possible version of this device. And the ratio of temperatures at the absolute scale for these reservoirs, the ratio of those temperatures is equal to the ratio of heat transfers. This is the maximum possible efficiency or performance. Can't say it's efficiency because it's typically greater than 1. This is the maximum possible performance for the refrigerators. This is the coefficient of performance for the refrigerator, if it's reversible, Carnot or otherwise. Okay, and then we talked just a little bit, and we've seen some problems. The heat pump is a refrigerator. The difference with the heat pump is where with the refrigerator I want to cool the refrigerated space. With the heat pump, what I actually want to do is I want to actually heat some other space. So I'm going to use the outside cold air, the low temperature air outside, to heat my higher temperature air inside. So it's the same first law, right? Same first law because it's the same device. The difference is the performance. What I want, the coefficient of performance for a heat pump, is this Q dot H, because that's what I want for a heat pump, is I want the Q dot H. To get that, I've got to put the power in. Okay? And if I plug this in, this guy, right? Plug this in and massage that, this becomes 1 over 1 minus QL over QH. Okay? Now, one thing to mention here, if I'm talking about a heat pump, because again, it's the same device, notice in a heat pump that this, what I want, is always going to be the sum of these two. This in, this plus this in equals this out. This is always greater than this, because this is always these two added together. So this is always greater than this. Coefficient of performance for a heat pump, always greater than 1. Coefficient of performance for a refrigerator, typically greater than 1, but this is always greater than 1. It always puts more heat into the high temperature space than the electricity we use to run it. That's the beauty of this device. Coefficient of performance for a heat pump, if it's reversible, again, just substitute in the ratio of absolute temperatures for the ratio of heat transfers. Okay? Alright, that in a nutshell is chapter 6. And as we saw, typically the worse these guys get, it's going to be basically some combination of, depending on the device, right, depending on which of these three devices we have, using these equations, the performance or the efficiency equation and the first law for the device. At most, they may give you conditions for one of these devices, and you have to use those conditions to figure out one of these unknown energy rates, and then use that in conjunction with these others to figure out some unknown quantity. That's about as complicated as these problems get. Don't underestimate them, but there's not too much involved there. Now, if we talk about, for us, Chapter 7, that is entropy and entropy balance and the second law. That's really the whole focus of Chapter 7, is a quick crash course into the second law of thermodynamics. The second law, our good friend Clausius comes to the conclusion that a change in entropy is always going to be greater than or equal to the heat transfer that causes that change in entropy divided by the temperature at which that heat transfer is occurring. That's a mouthful, but that is the second law in its purest, rawest, ugliest differential equation, differential inequality form. This is the second law. Now, what we normally do is we say, well, for a process from state 1 to 2, I integrate both sides of this equation. And if I integrate from 1 to 2, ds, that's greater than or equal to the integral from 1 to 2 del q over t. Well, integral ds is just delta s. This is just s2 minus s1 is going to be greater than or equal to this integral from state 1 to state 2 of all the heat divided by the temperature. So from 1 to 2, add up all the heat, add the heat in, subtract the heat out, divided by the temperature where every little slice of heat transfer occurs. Do that for the entire process from 1 to 2, and that will represent a quantity that is either less than or equal to the change in entropy. So what we normally do is we write this in an equation format, and we say, well, that change in entropy then is equal to this heat transfer that causes the change in entropy. And we know this quantity is always greater than whatever sum of heat transfer occurs. So what we do is we say, well, let's add the entropy that's being generated. So what we're saying here is entropy is always, there's always more entropy once we do something. There's always more entropy than what we started with. That's what this represents. This represents the entropy generated. Right? We cannot destroy, to the best of our knowledge, right, S-gen less than 0, negative entropy generation. This is what we call destruction. To the best of our knowledge is impossible. That's essentially kind of if we boil down the second law, it's essentially telling us, to the best of our knowledge, we cannot destroy entropy. Whenever we generate entropy, it's got to go somewhere in the universe. It cannot be destroyed, but we can and always do create it. Now, so something kind of interesting happens. If we have a reversible cycle, something kind of cool happens. Well, I happen to have a cycle over here, and I've got a couple of them. Let's go back to the heat engine. So if I've got a reversible cycle here, here's a reversible cycle, or if we consider the cycle to be reversible, and we say, well, change in entropy is going to equal the integral from 1 to 2, everywhere heat transfer occurs divided by the temperature, plus the amount of entropy generated. Well, if it's reversible, it's not generating entropy. Right? Reversible. And if it's a cycle, right, if I say that going into the turbine is 1 and coming out of the boiler is 2, the entropy here minus the entropy there is going to be 0. The entropy change is 0 for a cycle. So if I have a reversible cycle, this is 0, this is 0 because it's reversible and because it's a cycle. So that means 0 is equal to, we add up, well, we'll just write it here, equal 1 to 2 del Q over T plus 0. And we say, all right, well, let's go around this cycle then and add up everywhere heat transfer comes in at temperature and subtract everywhere heat goes out of the temperature. So we say, all right, well, 0 is equal to, here I've got heat coming in at a high temperature. So I've got QH over TH, that's positive because it's coming in. Here I've got heat going out. So it's QL going out at TL. So it's minus because it's going out. Plus 0. And notice what happens. This says QH over TH is equal to QL over TL, or QH over QL is equal to TH over TL. If we have a reversible cycle. And that's the reason these guys, remember these guys? We said if it's a reversible cycle, this becomes this. Here's why. Here's your proof. If we take the second law as true, here's your proof. Okay? It's a lot easier to prove that using the second law, for what it's worth. Okay? So that's kind of the basic idea there. Now, so if we go back, this is 5. So let's continue on with our discussion of the second law. All right, so we'll pick back up here. So again, second law. Page 6. The second law says the change in entropy we've talked about before. You should be taking notes. Sitting here watching me, I don't know how much you're going to get out of that. But if you do, fine. You don't have to take notes. I'm just telling you what I would do. I would try to trick my brain into realizing this stuff's important. And that if you force your brain to process it multiple ways, like writing it, hearing it, seeing it, and then writing it again, that tends to trick your brain into thinking this is important. Okay, anyway, let's keep going. This is the second law. These are all capital letters. We've seen this before. We can work this per unit mass. We divide everything here by m, so this is little s2 minus little s1 is equal to the integral of del little q over t plus little s gen. We can also work this per unit time. So that is m dot times little s2 minus little s1 is equal to the integral of del big Q dot over T plus, let's just say, big S gen dot, the rate at which entropy is being generated. Okay. They're all three the same equation. Which one do I use? Well, it depends on what you have. Right? I don't know. Depends on your problem. Depends on what you have. All right. I'm almost out of time. I'm just going to stop there, and we'll pick up on the next one. Hot.